Close your eyes for a moment and imagine standing on solid ground. Not Earth's ground, Venusian ground, but not the Venus we know today. The Venus of 3 billion years ago. Beneath your feet, warm basalt rock, still cooling from ancient lava flows. Above you, a sky not burning yellow, but pale, something closer to blue. The sun hangs lower on the horizon than you'd expect, because a day here lasts longer than an entire Earth year. The air around you is thick, but breathable, something like the humid, heavy weight of a tropical afternoon on Earth. And in the distance, the sound of water. Not acid rain evaporating before it touches the ground. Not volcanic gas. Actual liquid water moving across rock, pooling into something that might have once been a shallow sea. You're standing on a world that could have had all of this. And then something happened. Something so catastrophic, so complete, that today that same ground where you're standing would kill you in less than a second. Not from heat alone, though the heat would be enough. Not from pressure alone, though the pressure would be enough. From all of it, simultaneously. An environment that has essentially no parallel anywhere we've ever set foot. This is Venus, the planet most similar to Earth in size, in mass, in composition. The planet scientists sometimes call Earth's twin, and the story of what happened to it is the most terrifying cautionary tale in the entire solar system. From Earth, Venus doesn't look threatening. It's the brightest object in our sky, other than the sun and moon. You've seen it. You know it. That steady, unwavering point of light that appears just after sunset or just before dawn. The ancient Romans named it after their goddess of love and beauty because it was radiant, constant, serene. The reality beneath those clouds is something else entirely. Venus is the second planet from the Sun, orbiting at an average distance of about 108 million kilometers. It has a diameter of 12,103 kilometers, just 638 kilometers smaller than Earth's. Its mass is 81.5% of Earth's. Its surface gravity is 90% of what you feel right now. If you could stand on it without dying, you would weigh almost exactly what you weigh here. The similarities end there. The surface temperature on Venus averages 464 degrees Celsius. Hot enough to melt lead. Hot enough to melt zinc. Hot enough to make many metals flow like water. That's not the daytime high. That's the average on both the day and night sides, because the atmosphere transfers heat so efficiently that there is no meaningful temperature difference between noon and midnight on Venus. The atmospheric pressure at the surface is 92 times Earth's sea level pressure. To put that in terms your body understands, it's roughly the pressure you would feel standing 900 meters below the surface of the ocean. Not swimming there, standing there. The full column of a kilometer of water, pressing against every centimeter of you. And the atmosphere itself, 96.5% carbon dioxide, with dense clouds of sulfuric acid that wrap the entire planet, permanently, never breaking, not even for a moment. This is the world that orbits closest to Earth, of all the planets in the solar system. But here's the part that should genuinely disturb you. The chemical fingerprints of Venus's atmosphere tell a different story about where this world came from. Scientists first looked seriously at Venus's past in the 1980s. NASA's Pioneer Venus mission arrived in 1979, and among its measurements was something that would plant a seed of profound unease in planetary science for decades to come. The ratio of deuterium to hydrogen in Venus's atmosphere, the so-called D/H ratio, was approximately 120 times higher than in Earth's oceans. That number matters because of basic physics. Deuterium is a heavy isotope of hydrogen. When water molecules are broken apart by ultraviolet radiation high in the atmosphere, the lighter hydrogen atoms escape to space more easily than the heavier deuterium. Over billions of years, this process enriches the remaining atmosphere in deuterium. The more water a planet has lost, the higher the D/H ratio climbs. A ratio 120 times higher than Earth's suggests Venus may have once held enough water to fill shallow seas across much of its surface. That measurement alone launched decades of modeling. And what the models found is what makes the Venus story something far more than a geological curiosity. In a study published in Geophysical Research Letters, researchers at NASA's Goddard Institute ran climate simulations of Venus going back 4.2 billion years. Their conclusion, measured carefully, qualified properly, was this. Under the right initial conditions, Venus may have maintained liquid water on its surface and habitable temperatures for up to 2 billion years of its early history. 2 billion years. For context, life appeared on Earth somewhere around 3.5 to 4 billion years ago. If Venus had 2 billion years of potentially habitable conditions, this is in a world that briefly flirted with water before going dry. It's a world where, under conditions that planetary science considers physically plausible, life could have had as much time to develop as it did in Earth's earliest chapters. A 2023 study from the University of Chicago ran 94,080 separate simulations of Venus's atmospheric evolution. They found that of all those runs, only a few hundred produced an outcome consistent with Venus's atmosphere as we measure it today. And in those successful simulations, any habitable era had to end more than 3 billion years ago, with maximum ocean depths of around 300 meters across the entire surface. Shallow, probably restricted, perhaps intermittent. But water, on Venus, possibly for longer than multicellular life, has existed on Earth. So what happened? This is the question that drives an entire generation of planetary scientists. And the answer, as best we understand it today, involves a cascade of events that reinforce each other in a spiral, with no way out. The process has a name, runaway greenhouse effect. But the clinical precision of that phrase completely fails to capture what it actually describes. It begins with heat. Venus orbits 41 million kilometers closer to the Sun than Earth does. As the Sun gradually brightened over billions of years, as stars naturally do as they age, more energy reached Venus. The oceans began to warm. Warmer water evaporates faster. Water vapor is itself a greenhouse gas. So more vapor meant more heat trapped, which meant more evaporation, which meant more vapor. The atmosphere thickened with water. Ultraviolet radiation from the Sun began breaking those water molecules apart, high in the atmosphere where there was nothing to stop it. The lighter hydrogen atoms escaped to space. The oxygen that remained reacted with surface rocks, and the water was gone. With no water left on the surface, there was nothing to pull carbon dioxide out of the atmosphere. On Earth, a process called the carbonate-silicate cycle acts as a thermostat. Carbon dioxide dissolves in rainwater, forms carbonic acid, weathers rocks, and gets locked into minerals. Plate tectonics eventually subducts those minerals back into the mantle, releasing CO2 through volcanism in a slow, regulated exchange. Venus appears to have lost this regulation. Without liquid water, volcanic CO2 had nowhere to go. It built up in the atmosphere, and each molecule of CO2 trapped more heat. The surface temperature rose, and kept rising. Today, 96.5% of Venus's atmosphere is CO2. It presses down on the surface with such force that carbon dioxide at the surface is no longer technically a gas. It becomes a supercritical fluid, a state of matter that sits at the boundary between liquid and gas, and it creeps across the entire surface of Venus like an invisible sea, transferring heat with extraordinary efficiency. There's no corner of Venus's surface that is cool, no mountain high enough to escape, no polar region cold enough to offer refuge. The Maxwell Montes, the highest mountain range on Venus, rises about 11 kilometers above the surface, higher than Mount Everest. At its peaks, a mysterious reflective substance appears, something volatile that condenses in the slightly cooler temperatures there. Scientists aren't certain what it is. Possibly tellurium, possibly lead sulfide. The mountain is still hot enough to kill everything on Earth many times over. And then there are the clouds. Venus is permanently shrouded in 3 layers of cloud, extending from about 48 kilometers above the surface all the way up to 68 kilometers. It's dense enough to make the entire planet a mirror, reflecting roughly 85% of the sunlight that strikes them. From space, Venus appears as one of the brightest objects in the solar system, precisely because of these clouds. From below, they're a different story. Those clouds are composed primarily of sulfuric acid, not trace amounts, dense, swirling droplets of H2SO4, concentrated enough to dissolve metals over time. Acid rain does fall on Venus, but the extreme heat near the surface means it evaporates before it can reach the ground. The planet rains acid, and the acid never arrives. At the top of the cloud layers, winds move at up to 360 kilometers per hour. Those clouds circle the entire planet once every 4 Earth days. Even though the planet itself rotates far more slowly, the atmosphere moves faster than the world beneath it. Inside those hurricane-force cloud bands, something unexplained occurs. Dark streaks appear, persistent, stable structures that absorb ultraviolet radiation and maintain their shape, despite the chaos around them. Scientists have proposed several explanations. Fine particles, ice crystals, iron chloride. The streaks remain. And one possibility, considered by some astrobiologists and firmly contested by others, is that something is alive up there. In September 2020, a team of astronomers led by Jane Greaves at Cardiff University announced a detection that briefly restructured how science thought about Venus. Using the James Clerk Maxwell Telescope in Hawaii and later confirmed with ALMA in Chile, they reported finding traces of phosphine in Venus's upper atmosphere. Phosphine, pH 3, 1 phosphorus, 3 hydrogen. On Earth, this gas is produced in only 2 known ways: artificially in industrial laboratories, or by living organisms. Anaerobic microbes in swamps and wetlands, bacteria in the intestines of animals. Nothing in what we know of ordinary chemistry on a rocky planet should be producing it. The finding was immediately contested. Some analyses suggested the detection might actually be sulfur dioxide, a known Venusian atmospheric gas. Other telescopes initially failed to replicate it, but Greaves's team continued observing. In July 2023, Greaves announced that the team had detected phosphine again, twice. In new observations, they were able to look deeper into the atmosphere than before, finding traces not just at the cloud tops, but further down into the cloud deck itself. In July 2024, new data presented the most comprehensive observations yet. One observation run alone had generated 140 times as much data as the original 2020 detection. The phosphine signal, they reported, appeared again, and alongside it, something potentially even more significant: ammonia. On Earth, ammonia is produced almost entirely by biological processes. It's the waste product of nitrogen metabolizing bacteria. It's what makes compost smell the way it does. Finding it in Venus's atmosphere, at levels that shouldn't be chemically stable given the sulfuric acid environment, raised a different kind of question than phosphine did. We understand why ammonia might be useful to life, Clement said. If there is life on Venus producing ammonia, we have an idea why it might want to. Let's be precise about what this does and doesn't mean. No one has confirmed life on Venus. The phosphine detections are still debated. The ammonia findings are preliminary. There are abiotic explanations being seriously investigated. A 2021 paper from Cornell University proposed that explosive volcanic eruptions could be injecting phosphides from Venus's deep mantle into the atmosphere, where they react with sulfuric acid to form phosphine. In September 2024, preliminary analysis reconfirmed phosphine at a concentration of approximately 300 parts per billion, at around 55 kilometers altitude. The debate is not resolved. The instruments capable of actually settling it are not there yet. That is precisely why, in June 2021, NASA selected 2 new missions to Venus for the first time in 3 decades. Da Vinci will send both an orbiter and a descent probe directly into Venus's atmosphere. The probe will fall through the cloud layers, sampling gases as it descends, measuring the chemistry of an atmosphere that no human instrument has touched since the Soviet Vega probes in 1985. It will look directly at what Venus's air is made of and try to answer, among other things, what happened to the water. Veritas will orbit Venus and produce the most detailed radar maps of the surface ever made. It will look for evidence of current volcanic activity, measure the planet's topography with precision, and search for chemical signatures of what the surface is made of. ESA's Envision mission is scheduled for launch in December 2031. It will give scientists their first look at what lies beneath the volcanic plains. These 3 missions, if they all fly, will represent the most comprehensive study of Venus ever attempted. There's an important caveat. As of early 2026, proposed budget cuts at NASA have threatened both Da Vinci and Veritas. The situation remains in flux. Envision appears to be proceeding. Veritas and Da Vinci are fighting for survival. The answers they might find are worth fighting for. Here is what Venus asks you to sit with, if you're willing. 2 planets formed from the same swirling disk of gas and rock for 0.5 billion years ago, in the same neighborhood of the same average star. Same fundamental ingredients, same basic architecture. One became this: oceans, oxygen, a magnetic field that deflects the solar wind away from the atmosphere, seasons, weather, life. The other became a crushing, acid-soaked, airless furnace, where the rock at the surface behaves something like peanut butter beneath a thin chocolate shell. The difference between those outcomes is not large in cosmic terms. A slightly different orbit, a slightly different amount of water at the beginning, a slightly different rate at which the interior cooled, and weather plate tectonics took hold, small variations, compounding over billions of years into 2 completely irreconcilable worlds. And somewhere, possibly in a narrow band of clouds 50 kilometers above the inferno, where the temperature is around 30 to 60 degrees Celsius, where the pressure is close to what you feel right now, where sulfuric acid floats in droplets through air moving at hurricane speed. There may be something adapted, surviving in a refuge suspended above a planet that has been uninhabitable for over 3 billion years, evolved, perhaps, from life that existed when Venus had oceans, retreating upward as the surface transformed, finding the only zone still tolerable. Or there may be nothing. The phosphine could be volcanism. The ammonia could be chemistry we don't yet understand. The dark streaks in the clouds could be particles. Venus could have burned clean. We don't know yet. But consider what it means. Either way, if there is nothing alive on Venus, then we are witnessing what Earth might have become under different initial conditions. Our twin, our warning, the answer to what lies at the end of the path we're currently accelerating down with our own greenhouse gases. If there is something alive, then life is not a rare accident on a single fortunate world. Life is something that finds its way even into the surviving margins of a catastrophe, even in the ruins of what was once a habitable planet, even 50 kilometers above a surface that has been a furnace for 3 billion years. Both possibilities are staggering in their implications. Venus has been watching us since the first humans looked up and noticed that beautiful, steady light in the evening sky. For all of human history, we thought it was the goddess of love. It may have been a mirror all along. I hope this gave you new perspective on our closest planetary neighbor. If you enjoyed it, consider subscribing. I'll see you in the next one.